Today we are going to continue with current electricity. This is the structure of a galvanometer. We have the iron core and a rectangular coil is wound round it. The spiral spring, the horseshoe-shaped magnet, the angular scale on which the pointer moves. The magnetic field due to the horseshoe-shaped magnet and the magnetic field due to the current flowing through this rectangular coil interacts with each other, producing a shift in this pointer, which indicates the current. Current is directly proportional to the pointer movement. The more is the current, more is the movement of the pointer on the scale. This galvanometer is used to convert into ammeter and voltmeter. This is the representation of this galvanometer or moving coil galvanometer. The position of the pointer on the scale indicates the current passing through the galvanometer or the potential difference across it. Hence, this galvanometer used as ammeter or voltmeter with some modification. Resistance of the galvanometer is generally 100 ohms and has a capacity of 1 milliampere. Let us see how to convert this moving coil galvanometer into an ammeter. So this is our galvanometer. To it, we connect a shunt resistance S in parallel or across it. R is the external resistance of this external circuit. Now let us see the modifications necessary to convert a galvanometer into ammeter are: the current capacity has to be increased to the desired value. Since ammeter is connected in series with a circuit, the effective resistance of the galvanometer and shunt should be as small as possible. There should be sufficient protection from the damages due to excess current. Thus, a low resistance connected in parallel with the galvanometer is called shunt. A shunt is connected to the galvanometer to increase the range of the ammeter. The resistance is decreased between the points of contact. Part of the current is diverted through the shunt, thus avoiding damage due to excess current. To convert a moving coil galvanometer in ammeter, we have the following equations. The voltage across the galvanometer and the shunt are same because they are connected in parallel. Therefore, voltage across the galvanometer is GIG, which is equal to the voltage across the shunt, that is SIS. Therefore, GIG is equal to S into I minus IQ, because as we can see, the current I gets divided into IG and IS. Therefore, the shunt required is given by the equation S is equal to IG upon I minus IG into G. If I is equal to N into IG, we can substitute this equation and get S is equal to again G upon N minus 1, where N is equal to I upon IG. Now let us see how to convert this moving coil galvanometer into a voltmeter. This is the galvanometer which is connected to a high resistance X. R is the external resistance across which the voltage is V, which is measured. Thus, the modifications required are: the voltage capacity has to be increased to the desired value. Its effective resistance should be more. Protection from damage due to excess potential difference must be taken care for. a voltmeter is connected in parallel with the circuit, it should draw as less current as possible. So voltmeter should have high resistance. Thus, a high resistance capital X of suitable value is connected in series with the galvanometer. Now let us see the equations to convert a galvanometer into a voltmeter. The total voltage V is equal to the potential difference across X, that is IGX, plus the potential difference across the galvanometer, which is IgG. Therefore, IGX is equal to V minus IgG. Capital X is equal to V upon Ig minus G. Now, if V is equal to NV into Ig, capital X is equal to given by G into NV minus 1. Now let us see what is thermoelectricity. Here we have a typical thermocouple of bismuth and antimony, Bi and Sb. Two junctions are kept in two separate temperatures, the hot junction and the cold junction, which is connected to a galvanometer to detect whether current flows through it or not. Electric current, we know, when it passes through conductor, it gets heated up. Therefore, it gets converted to thermal energy. The reverse process, that is thermal energy converting to electrical energy, is called thermoelectric effect. This was discovered by Seebeck and hence it is known as Seebeck effect. Thus, if two different metals are joined to form a closed loop and these junctions are kept at different temperatures, an EMF is developed known as thermo-EMF. The pair of dissimilar metals is known as thermocouple. This effect is reversible. The direction of current is reversed if the hot and the cold junctions are interchanged. The equations involved the thermo-EMF developed in a thermocouple when the cold junction is at 0 degrees Celsius and the hot junction at T degrees Celsius is epsilon is equal to alpha T plus half beta T square. Alpha and beta are known as thermoelectric constants. The equation represents the equation of a parabola. Another example of a thermocouple is a copper-iron junction. So that's it. Thank you.